Arbitrarily good approximations to knapsack problems. Often when you talk to someone faced with an NP-hard optimization problem, they are hoping you can give them something that will produce a solution within, say, 1% of the optimum, or at least within a small percentage of optimal. Viewed from this perspective, the approximation algorithms we've seen thus far come across as quite weak. Solutions within a factor of 2 of the minimum for center selection and vertex cover, i.e. 100% more than optimal. The set cover algorithm in section 10.3 is even worse. Its cost is not even within a fixed constant factor of the minima possible. Here is an important point underlying the state of affairs. NP-complete problems, as you well know, are all equivalent with respect to polynomial time solvability, but assuming P is not equal to NP, they differ considerably in the extent to which their solutions can be efficiently approximated. In some cases, it is actually possible to prove limits on approximability. For example, if a P is not equal to NP, then the guarantee provided by our center selection algorithm is the best possible for any polynomial time algorithm. Similarly, the guarantee provided by the set cover algorithm, however bad it may seem, is very close to the best possible, unless P is equal to NP. For other problems, such as the vertex cover problem, the approximation algorithm we gave is essentially the best known, but it is an open question whether there could be polynomial time algorithms with better guarantees. We will not discuss the topic of lower bounds on approximability in this book, while some lower bounds of this type are not so difficult to prove, such as for center selection. Many are extremely technical. The problem in this section, we discuss an NP-complete problem for which it is possible to design a polynomial time algorithm, providing a very strong approximation. We will consider a slightly more general version of the knapsack or subset sum problem. Suppose you have n items that you consider packing in a knapsack. Each item I equals to 1 to 3 until n has two integer parameters, a weight wi and a value vi. Given a knapsack capacity w, the goal of the knapsack problem is to find a subset S of items of maximum value subject to the restriction that the total weight of the set should not exceed W. In other words, we wish to maximize the summations of Vi summing for all I in S subject to the condition that the summations of Wi summing for all I in S is less than or equals to W. How strong an approximation can we hope for? Our algorithm will take as input the weights and the values defining the problem and will also take an extra parameter epsilon, the desired position. It will find a subset S whose total weight does not exceed W, with a value the summations of Vi summing for all I in S at most a 1 plus epsilon factor below the maximum possible. The algorithm will run in polynomial time for any fixed choice of epsilon which is greater than 0. However, the dependence on epsilon will not be polynomial. We call such an algorithm a polynomial time approximation scheme. You may ask, how could such a strong kind of approximation algorithm be possible in polynomial time when the knapsack problem is NP-hard? With integer values, if we get close enough to the optimal value, we must reach the optimum itself. The catch is in the non-polynomial dependence on the desired position for any fixed choice of epsilon, such as epsilon equals to .5, epsilon equals to .2, or even epsilon equals to .01. The algorithm runs in polynomial time, but as we change epsilon to smaller and smaller values, the running time gets larger. By the time we make epsilon small enough to make sure we get the optimal value, it is no longer a polynomial time algorithm. Designing the algorithm in section 6.4, we consider the algorithms for the subset sum problem, the special case of the knapsack problems with when Vi is equal to Wi for all items I. We gave a dynamic programming algorithm for this special case that ran in big O of n W time, assuming the weights are integers. This algorithm naturally extends to the more general knapsack problem. See the end of section 6.4 for this extension. The algorithm given in section 6.4 works well when the weights are small even if the values may be big. It is also possible to extend our dynamic programming algorithm for the case when the values are small, even if the weights may be big. At the end of this section, we give a dynamic programming algorithm for that case, running in time big O of n squared times v star, where v star is the maxima chosen among all possible vi with index I. Note that this algorithm does not run in polynomial time. It is only pseudo-polynomial because of its dependence on the size of the values vi. Indeed, since we proved this problem to be NP-complete in Chapter 8, we don't expect to be able to find a polynomial time algorithm. Algorithms that depend on the values in a pseudo-polynomial way can often be used to design polynomial time approximation schemes, and the algorithm we developed here is a very clean example of the basic strategy. In particular, we will use the dynamic programming algorithm with the running time, big O of n squared times v star, to design a polynomial time approximation scheme. The idea is as follows. If the values are small integers, then v star is small and the problem can be solved in polynomial time already. On the other hand, if the values are large, then we do not have to deal with them exactly as we only want an approximately optimal solution. We will use a rounding parameter b, whose value we'll set later, and we'll consider the values rounded to the integer multiple of b. We will use our dynamic programming algorithm to solve the problem with the rounded values. More precisely, for each item I, let its rounded value to be vi wave, which is equals to the 4 functions with input vi divided by b. Then after we take the floor function, we multiply by b again. Note that the rounded and the original value are quite close to each other. (11.34) For each item I, we have vi which is less than equals to vi wave, which is less than equals to vi plus b. What did we gain by the rounding? If the values were big to start with, we did not make them any smaller. However, the rounded values are all integer multiples of a common value b. So instead of solving the problem with the rounded value vi wave, we can change the units. We can divide all values by b and get an equivalent problem. Let vi hat equals to vi wave divided by b, which is equals to the output of the ceiling functions with input vi divided by b for all index I starting from 1 to 3 until n. 11.35. The knapsack problem with values vi wave and the scaled problem with the values vi hat have the same set of optimal solutions. The optimal values differ exactly by a factor of b, and the scaled values are integral. Now we are ready to state our approximation algorithm. We will assume that all items have weight at most w, as items with a weight wi which is greater than w are not in any solution and hence can be deleted. Knapsack approx of epsilon. Set b equals to epsilon divided by n times the maxima of vi, where the maxima is taken among all possible index I, and solve the knapsack problem with values vi hat equivalently vi wave. Then we return the set S of items found. Analyzing the algorithm, first note that the solution found is at least feasible. That is, the summations of wi is less than equals to w, summing for all index I in S. This is true as we have rounded only the values and not the weights. This is why we need the new dynamic programming algorithm described at the end of the section. 11.36. The set of items S returned by the algorithm has total weight at most w. That is, the summations of w I, summing for all index I in S, is less than equals to w. Next, we will prove that this algorithm runs in polynomial time. 11.37. The algorithm Knapsack Approx runs in polynomial time for any fixed epsilon greater than 0. Proof. Setting b and rounding item values can clearly be done in polynomial time. The time-consuming part of this algorithm is the dynamic programming to solve the rounded problem. Recall that for problems with integer values, the dynamic programming algorithm we use runs in time big O of n squared times v star, where v star is the maxima taken among all possible vi with index I. Now we are applying these algorithms for an instance in which each item I has weight wi and a value vi hat. To determine the running time, we need to determine the maxima of vi hat, where the maxima is taken among all possible index I. The item j with a maximum value vj, which is equals to the maxima of vi, also has a maximum value in the rounded problem. So, that is, the maxima of vi hat with all possible I is equals to vj hat, which is equals to, by the definition, is the output of the ceiling functions of vj divided by b, which is equals to n times epsilon to the inverse. Hence, hence the overall running time of the algorithm is a big O of n cubed times 1 over epsilon. Note that this is polynomial time for any fixed epsilon greater than 0 as claimed, but the dependence on the desired precision epsilon is not polynomial, as the running time includes epsilon to the minus 1 rather than log of epsilon to the minus 1. So it's not a polynomial. Finally, we need to consider the key issue. How good is the solution obtained by this algorithm? Statement 11.34 shows that the values vi wave we used are close to the real values vi, and this suggests that the solution obtained may not be far from optimal. 11.38. If S is the solution found by the Knapsack Approx algorithm, and S star is any other solution satisfying the summations of Wi summing for all I in S star less than equals to W, then we have 1 plus epsilon times the summations of Vi summing for all I in S is greater than equals to the summations of Vi summing for all I in S star. Proof. Let S star be any set satisfying the summations of Wi summing for all I in S star, which is less than equals to W. Our algorithm finds the optimal solution with the values Vi wave, so we know that the summations of Vi wave summing for all I in S is greater than equals to the summations of Vi wave summing for all I in S star. The rounded value Vi wave and the real values Vi are quite close by 11.34, so we have get the following chain of inequalities. The summations of Vi summing for all I in S star, the optimal solution, is less than equals to the summations of Vi wave summing for all I in S star, because this is the optimal solution with value Vi wave, which is less than equals to the summations of Vi wave summing for all I in S, and which is less than equals to the summations of Vi plus B summing for all I in S, because by the definitions of Vi divided by B, taking the ceiling function, then multiply by the B back. So which is less than equals to n times B plus the summations of I in S summing for all Vi, because if we summing for all B summing for all index I in S, then the size of S should be less than n. So that will be the term m times b. So these inequalities on the leftmost hand side is the summations of vi summing for oi in S star, and the rightmost side is n times b plus the summations of vi summing for oi in S. So we know that there's a bound between the summations of vi summing for oi in S star and the summations of vi summing for oi in S. Showing that the value of the summations of vi summing for oi in S of the solution we obtained is at most mb smaller than the maximum value possible. We wanted to obtain a relative error showing that the value obtained, the summations of vi summing for oi in S, is at most a 1 plus epsilon factor less than the maximum possible, so we need to compare mb to the value the summations of vi summing for oi in S. Note that by our choice of the value b, the item j with the largest value satisfies vj equals to vj wave. By our assumption that each item alone fits in the knapsack, that is wi, which is less than or equals to w for all items I, we get that the summations of vi summing for all I in S is greater than or equals to vj wave, which is the maxima of vi, where the maxima is taken among all possible I, and hence mb is less than or equals to epsilon times the summations of vi summing for all I in S. Using this bound, we conclude with the summations of vi summing for all I is in S star is less than or equals to the summations of vi summing for all I in S plus mb, which is less than or equals to 1 plus epsilon times the summations of vi summing for all I in S, which is as claimed by 11.38. Now we will introduce the new dynamic programming algorithm for the knapsack problem. To solve a problem by dynamic programming, we have to define a polynomial set of subproblems. The dynamic programming algorithm we defined when we studied the knapsack problem earlier used subproblems of the form OPT of IW, the subproblem of finding the maximum value of any solution using a subset of the items 1, 2, 3 until I, and a knapsack of weight W. When the weights are large, this is a large set of problems. We need a set of subproblems that work well when the values are reasonably small. This suggests that we should use subproblems associated with values, not weights. We defined our subproblems as follows. The subproblem is defined by I and a target value V, and the OPT bar of IV is the smallest knapsack weight W, so that one can obtain a solution using a subset of items, the set 1, 2, 3 until I, with a value at least V. We will have a subproblem for all I equals to 0, 1, 2, 3 until n, and the values capital V equals to 0, 1, 2, 3, and so on until the summations of Vj starting with index starting from 1 to I. All of them are integer values. If a V star denotes a maxima of Vi summing for index I, then we see that the largest V can get in a subproblem is summations of Vj summing for all index j starting from 1 to n is less than or equals to n times V star. Thus, assuming the values are integral, there are at most big O of n squared times V star subproblems. None of these subproblems is precisely the original instance of knapsack, but if we have the values of all subproblems OPT bar of mv for v starting from 0, 1, 2, 3, and so on until the summations of vi summing for index I, then the value of the original problem can be obtained easily. It is the largest value, capital V, such that the OPT bar of a n v is less than or equals to w. It is not hard to give a recurrence for solving these subproblems. for solving this subproblem. By analogy with the dynamic programming algorithm for subset sum, we consider cases depending on whether or not the last item is included in the optimal solution for subset sum. We consider cases depending on whether or not the last if n is not in O, then opt bar of mv is equals to opt bar of n minus 1 v, because we can exclude the item n. Subcases. The second subcase is if n is in O, not in O, the only item in O, then opt bar of mv is equals to wn. This is very trivial. Equals to opt bar of third case, if n is in O and is not the only item in O, then opt bar of mv is equals to wn plus opt bar of m minus 1 is the only item in O, then opt bar we have to calculate the optimal solution to wn, the weight of n. The inclusions of the last item. The third one is if n is these last two options can be the only item in O, compactly opt bar of if n is in O, then opt bar of mv is equals to wn the opt bar of m minus 1 and v minus 1 vn, and because the maxima chosen we only include the item vn. But we have to find the optimal solution for all those previous items. Analog. So these of the last two options can be summarized chapter 6. More compactly as if n is greater than the summations then of opt bar of mv is equals to wn plus opt bar of mv is equals to wn plus either m minus 1 or v minus vn. Opt bar of m minus 1 and maxima chosen among 0 and v minus chosen among opt bar so of this implies the following and wn plus opt bar of m minus 1 analogy, and maxima chosen between 0 and v minus vn. Now we can write down the analogous dynamic programming algorithm. So knapsack of n is an array starting with m is an array of a two-dimensional array starting with the rows starting with 0, 1, 2, 3 until n, and the columns starting with 0, 1, 2, 3 until capital V. Now for I starting from 0, 1, 2, 3 until n, this is the index for the row. We set m of I0 equals to 0. This is the initialization. So after we break out the for loop of the initialization, we do another for loop where the outer for loop is index starting from 1 to 3 until n, and the inner for loop is starting for v starting from 1 to 3 until the summations of vj, summing with index j starting from 1 to I, the maximum possible values. If v is greater than the summations of vj, summing with index j starting from 1 to I minus 1, then m of iv is equals to wi plus m of I minus 1v, else m of iv is equals to the minima chosen among m of I minus 1v and wi plus m of I minus 1 and maxima chosen among 0 and v minus vi. Now we break out this double for loop. Then we return the maximum value v such that m of mv is less than equals to w. Now 11.40, knapsack of n takes big O of n squared times v star time and correctly computes the optimal solution values of the subproblems. So as was done before, we can track back through the stable M containing the optimal values of the subproblems to find an optimal solution.